Good evening. I'd like to thank you all for coming to the first event JHU Humanity Plus is running this year. I'm Craig Borson, the president of the organization. We're a new student group on campus, and we're interested in discussing, how what it means to be human might change in the future, especially in light of the ever startling pace of technological progress. And importantly, we're also interested in sort of what humanity should become. And I guess in this sense, we act as an ethical or a bioethical forum. If you're interested in hearing about future events that we'll be holding on campus, please sign up for our newsletter. It's just available at jhuhplus.com. Tonight, it's our pleasure, along with Prometheus, to welcome Dr. Aubrey to talk about his ideas regarding human aging. Dr. DeGray is a biomedical gerontologist based in Cambridge in the United Kingdom. He is Chief Science Officer of SENS Foundation, a California-based charity dedicated to combating the aging process. He is also Editor-in-Chief of Rejuvenation Research, the world's highest impact peer-reviewed journal focused on intervention in aging. He received his BA and PhD from the University of Cambridge in 1985 and 2000, respectively, and he's a fellow of both the Gerontological Society of America and the American Aging Association, and sits on the editorial and scientific advisory boards of numerous journals and organizations. He has been engaged in the field of biogerontology since the mid-1990s, and his research interests encompass the characterization of all the accumulating and eventually pathogenic molecular and cellular side effects of metabolism that constitute mammalian aging. Importantly, he's also interested in the design of interventions to repair and prevent that damage. He has developed a possibly comprehensive plan for such repair, termed Strategies for Engineered Negligible Senescence. And now, ladies and gentlemen, without further ado, it is a great pleasure for me to introduce you, Dr. Aubrey DeGray.
Thanks very much, Craig, and thank you all for coming. Yes, it's a great delight to be here. Actually, we were just talking earlier, and this is actually the first time I've been to Johns Hopkins. It's rather surprising that I haven't been here before, but I'm delighted to be here now. And I'm delighted also that we have a nice long time tonight. I gather the schedule is going to allow me to give a pretty comprehensive talk. I'll probably talk for just on an hour, following which we will have really as long as we like for Q&A, so to speak. And of course, I'm totally happy to engage in discussion of anything I say, and indeed anything I may leave out. So let's hope for the best. I gather that we can turn the stage lights out, so if you can see the screen a bit better. I think that's going to work well. Very good. So here we go. This is the title of my talk, as you can see. It's quite dramatic. I really think that it's not an exaggeration, that we have a respectable chance of defeating aging with regenerative medicine in the foreseeable future, and I'll be telling you all about why I think that and details about what it really means. SENS Foundation, the organisation I work for, is, as you just heard, a charity based in the USA, based in California in fact, a regular public charity, a 501c3, and we work to try to develop these regenerative medicine therapies against aging, and also we do a whole bunch of other things in that context, outreach, other things like that, so as to make sure that these therapies are not simply developed but also made available. And that's our mission statement, so to speak. So most of what I have to say will be how we're going to go about combating aging. But I thought I would start with a few minutes about how important this problem is, why it has been my choice to dedicate my life to it, and why you should dedicate your life to it too. It starts here, really. It starts with numbers. A lot of people, especially a lot of non-biologists, have a mistaken view, a genuinely incorrect view about what it means to die of aging. A very common view is that dying of aging is what you want to happen, in the sense that it's what happens if you avoid all of the diseases and disabilities that we're very familiar with in old age and that we don't want, like Alzheimer's and cancer and cardiovascular disease and such like. And therefore, if you avoid these, you live a reasonably good innings, and you eventually keel over, perhaps in your sleep, having lived, and been relatively healthy for your age during those declining years. But that's actually a completely mistaken view, because we have to ask ourselves, why are the diseases of old age diseases of old age? Why don't they affect young adults? And of course the answer is that there are aspects of the later stages of a process that does go on throughout life and that is initially harmless, that process being aging. So, in fact, if you die of Alzheimer's or you die of cardiovascular disease or whatever, then you do die of aging. Therefore, we can actually ask the question, how many people die of aging in that context? And the answers that we get are summarized here. Of the roughly 150,000 people that die each day worldwide of all causes added together, more or less 2/3 of those people die of aging. That's an awful lot. That's 100,000 people a day. In the Western world, in the developed world, the proportion is of course a great deal higher. It's around 90%, because not many people in the USA die of malaria, for example. So, it's pretty unequivocally humanity's worst problem. Because, I mean, it's not just the death, of course, it's also the suffering that's involved. The fact that most people who die in old age do so only after a fairly long period of debilitation and decrepitude and dependence and general misery. So, we'd better fix it, really. Plus also, I mean, even if you don't get the disease, what part of this is it hard to understand? Even if you don't get the diseases of old age, so, even if the guy on the left is about to have his head bitten off by a shark, so what really? So this is why we do this. Now, Craig mentioned at the beginning that this talk is co-sponsored by Prometheus, which I gather is the university's philosophical society. And, of course, there is a lot of interest from ethicists about this question of whether it would be a good thing to develop, really medicine that actually works against aging. I don't have much time for that debate, to be perfectly honest, and I'm going to tell you why. I don't think it. I think it is a distinct euphemism to call it a debate at all. The fundamental reason I think that is something that I want you to be absolutely, all of you, I want you to be absolutely sure to understand throughout this talk. I actually don't work on longevity. The SENS Foundation doesn't work on longevity. We work on health. We work on stopping people from getting sick. The only difference between what SENS Foundation does and what the whole of the rest of the medical profession does in terms of medical research is that we think that we've got a way in the foreseeable future that's got a good chance of working so well against aging that it will have a side effect, a big side effect in terms of the consequential length of time people will live. Because the fact is, the reason why people die mainly at the age of 70 or 80 is because of aging, obviously. So if we can truly stop that, if we can truly make people stay, however long they live, as healthy as you in the audience are, as healthy as young adults, then we are likely to have a consequence of people continuing to have the low probability per year of death that they have as young adults. And that means they'll live a lot longer. So that's a very important thing to bear in mind. We are not talking here about therapies that will keep people alive in a bad state of health for a lot longer than they currently are. We are talking about therapies which will keep people in a good state of health, not just a good state of health, but a perfect state of health, and thereby will cause them to live longer. Now, the other thing I want to emphasize, which is really all I have to say about the so-called ethical debate on this matter, is that we don't know what the future's going to be like in other ways. So it's very easy and very common for people, when confronted with the idea that we might develop these medicines, to respond with knee-jerk reactions along the lines of, oh dear, where would we put all the people, or won't dictators live forever, or how will we pay the pensions, and such like. Now, it's very important to understand that those are legitimate concerns in principle, but that we simply can't answer the question, how could society, address such things? We just don't know the context within which society, given such therapies, would address these things. If we just take overpopulation, for example. We just don't know how many kids people are going to want to have, or at what age they're going to want to have them, or for that matter, what other technologies may have been developed in decades to come that will reduce the impact of a given person on the environment and thereby increase the number of people that we can have on the planet without doing too much harm. So there's an incredible number of things we don't know. And what we, in my view, have an absolutely clear moral obligation not to do is to think to ourselves, oh dear, well, we're terribly clever. We know that humanity in the future is going to suffer if it has these therapies, therefore we are not going to develop them. Because if we do that, if we take that view and we're wrong, then 30 or whatever years down the road, humanity of the future is not going to be very happy with us, is it? It's going to think that we were really not very clever at all, to think that we knew what life was going to be like, and in fact to suppose that there were going to be problems that in fact didn't turn out to exist. So to my mind, that is the beginning and end of the so-called ethical debate on the question of whether we should develop all this. Alright, so, as I said, I'm going to spend the rest of my time talking about how we're going to do this. And I'm going to split my remarks into quite a number of sections. First of all, I'm going to give a reasonably detailed and careful 30,000-foot view of the whole thing. I'm going to describe what aging is. I'm going to describe a bunch of possibilities for how, in principle, we might go about defeating aging with medicine or postponing aging with medicine. And I'm going to describe why one of those ways seems to me to be a great deal more promising than the others. Then in the second step, I'm going to go into more detail about that about that preferred approach to combating aging. I'm going to describe how it breaks down into a bunch of sub-problems. And that's going to be where I start talking real biology rather than just talking rather somewhat in the abstract as I will initially. Then I'm going to go a bit further. I don't know how many of you in the audience are studying biology, but I know that those of you who are will want to be convinced that what I'm saying here is actually based on proper established facts and how we can actually develop a real project plan, so to speak here. What sort of existing data, existing knowledge, existing technology we're starting from, and how we propose to go from there to the eventual implementation of all of this. And you'll be pleased to hear that the amount of detail that there is that would need to be described in order to give you a full account of all of that is far more than I could possibly get through in just 1 hour. So what I'm actually going to do instead, I'm going to just talk about one of these 7 components that I will have just introduced, and I'm going to go through and tell you a bit about it and about what SENS Foundation is doing in that area and how well it's going. If you want to know more, I wrote a book a few years ago called Ending Aging, which goes into all of this in humongous detail. There's a whole chapter on each of the various component therapies that we're going to need to develop. And it's written in a manner that a non-specialist, a non-biologist should be able to understand, but it doesn't leave anything out either. So that's going to be the real hardcore biology component of this talk. Then after that I'm going to go into talking about the longer term future, and I'm going to be introducing a concept that I've called longevity escape velocity, which I will leave you in suspense about until then. But basically I'll be talking about what's going to happen in the longer term. And longevity escape velocity is such an important concept that I'm not only going to introduce it, I'm going to spend a little while talking in the next part about why it's a realistic concept. And then finally, right at the end, I'm going to spend a minute or two just discussing how everyone here, whatever you study, can potentially make a difference in this area, can actually help to hasten the time at which we actually have these therapies in place. All right, so I'm going to start with the 30,000-foot view. And in order to start, I'm going to go back to the mission statement that I put up earlier, this business about applying regenerative medicine to aging. And I'm going to define those 2 terms, because it's important to have quite precise definitions of those terms in order to really understand what this is all about. Regenerative medicine. Now, regenerative medicine, you've probably heard of it. You probably know that stem cell therapies are a big part of regenerative medicine. And you've probably also heard of tissue engineering, which is another big part, the creation of artificial organs in the laboratory and their use for transplantation. They are very important components, but they are only components of regenerative medicine. If we want an overall, completely spanning definition of regenerative medicine, you need something like what I've written here. Any intervention that seeks to restore the structure of a tissue or an organ, or the whole body for that matter, to how it was before it suffered some kind of damage. And there are a couple of features of that definition that I want to highlight before going on. First one is the type of damage. A lot of you have probably become familiar with regenerative medicine in the context of its application to acute injury, like, spinal cord trauma, or someone having the tip of their finger chopped off, or something like that. And that's certainly very important, but it's not necessary that it should be that type of damage. One could equally, in principle, apply regenerative medicine to repairing chronic, gradually accumulating, long-term damage of the sort that we see in aging. Second thing I want to highlight is the scale of all this. So, tissue engineering is clearly, by definition, the creation of a whole new organ outside the body and its introduction into the body. Stem cell therapy, on the other hand, is not at the organ level, it's at the cellular level. We inject, typically, depending on the organ we're trying to repair, we inject stem cells into the bloodstream and they go to the right place and do the fix. But that's at the cellular level. But that's not all we could do in principle. We could also have molecular level regenerative medicine, where cells that are already in the body and are still alive and everything, but not functioning right, have something wrong inside them, and we go in and fix that. We repair the inside of a cell that's actually there in situ. And it turns out that that's quite an important thing to take into account when we get into talking about what regenerative medicine for aging would actually look like. Okay, that's regenerative medicine. What about aging? Well, there are lots and lots of definitions of aging out there. I mean, really a lot. And most of them are pretty good, they're pretty uncontroversial, but most of them are pretty useless when what you want is a way of orienting your thoughts around the question of how we might develop interventions against aging. Most of them just don't help with that. So here's a definition that I really like because it does help. And here I'm saying a couple of important things. First of all, I'm saying metabolism eventually causes pathology. Now that's really just a technical way of saying aging is a side effect of being alive in the first place. Metabolism is the word that biologists use not only to denote oxygen consumption, so that the term metabolic rate that you may have come across means the rate at which we consume oxygen. Metabolism is used to encompass all of the molecular and cellular and systemic processes that go on in our bodies all the time and keep us going as long as we do, from day to day or from year to year. That's metabolism. Pathology is the word I'm going to use to denote all of the things that go wrong in old age. So all the diseases, some of which I mentioned earlier, of course, and also all of the things that we don't necessarily call diseases, but which still go wrong. So let's say decline of function of the immune system. So metabolism eventually causes pathology. You knew that, but obviously it's a fundamental feature that has to exist for any definition of aging. But the other thing that I'm mentioning here is perhaps a little bit less obvious and very important. So I absolutely want to focus on this and make sure that you understand what I'm saying. It's going to be critical for the rest of the talk. I'm introducing this word damage in this definition. And I'm using the word damage in this very precise way to denote the set of intermediates between metabolism and pathology. There has to be some way in which metabolism does eventually cause pathology, but doesn't cause it at first. And damage is the answer to that. Damage is the mediators of metabolism causing pathology. The set of molecular and cellular changes that happen in the body throughout life, even starting before we're born, and the other key feature is they accumulate. So damage is side effects of metabolism that happen throughout life and accumulate. And because they accumulate, eventually they accumulate to a sufficient level of abundance that they get in the way. And they start to impair the function of metabolism, and you end up getting pathologies emerging and progressing. So that's the definition I'm going to use for aging. So I've been quite laboured about that. I've made sure that you understand it. And the reason I mentioned it is because it's a really useful definition for orienting our thoughts about what to do about aging. What do I mean by that? Well, this is basically what I mean. Historically, there have been two major themes, major ways in which people have considered the possibility of doing something serious about aging. I'm going to call those methods the gerontology approach and the geriatrics approach. So the geriatrics approach encompasses pretty much everything we have today in terms of medicine for the pathologies of old age. And the way we can describe it really is that it consists of treating the diseases of old age just like any other disease, characterizing the symptoms and trying to get rid of the symptoms without too much a focus on how that disease actually arose. Now, that's basically the reason why geriatric medicine is not very useful, it's not very good. Because as you can see very clearly from this formalization, the problem is that the geriatrician's job is getting progressively harder all the time as the patient gets older, because the precursors, the causes of the geriatrician's target, are continuing to accumulate. In other words, the damage is accumulating and the pathology, which is the geriatrician's target, is thereby becoming harder and harder to actually address. So yeah, I mean, the geriatrics approach to combating aging is better than nothing, but it's not much better than nothing. And really, even in principle, it never can be. You know, we've got all these things that go wrong with us during life, and during aging, during late life, and they exacerbate each other, they interact. It's just a completely hopeless, intractable downward spiral. So the geriatrics approach is not the way to go. And a number of people over the years have known this, and have decided they wanted to do something about it, and their thought was, let's adopt the very effective and powerful maxim that prevention is better than cure. Let's just try and intervene at an earlier stage in the chain of events, and thereby perhaps we can have more of an effect. So in this case what that means is, let's clean up metabolism. Let's try and reduce the rate at which metabolism actually creates the damage of old age, and thereby, of course, postpone the age at which the damage reaches a level of abundance that is pathogenic. So that sounds much more hopeful, doesn't it? And indeed, in principle, I think that the gerontology approach could substantially postpone the pathologies of old age. But only in principle. Here's why. There's another problem. Metabolism is very, very, very complicated. This here is a simplified diagram of a small subset of what we know about how metabolism works. And as you can see, it's fairly hairy. That's bad enough, but actually it's much worse than that. The real problem is that this is a simplified diagram of a small subset of what we know about how metabolism works, which, as any biologist will tell you, is utterly and completely dwarfed and overwhelmed by the astronomical amount that we don't know about how metabolism works, even ignoring all the stuff that we don't even know that we don't know. So, this is an approach that could work in principle, but it's an approach that emphatically whose time has not come. So, yes, in principle, but we've got to know an astronomical amount more than we currently do about how the body, how cells even actually work before we can make this fly. All right, well that sounds pretty grim. So what's left? I mean, of course, if that were the end of my story, I wouldn't be standing here. So there must be something more, and luckily there is. I'm going to, in order to introduce it, I'm going to start with an analogy. I'm going to start talking a little bit about cars. And the reason I'm going to do that is because the human body is a machine. I mean, it's a really, really complicated machine, we knew that, but it's still a machine. Which means that, in principle, we might be able to get some good clues about how to extend the healthy, fully functioning longevity of this machine, the human body, by looking at how we already successfully extend the healthy, functioning lifespan of simple man-made machines like cars. Right? That's the concept. All right then, so how do we do it? Well, this is a car that is more than 50 years old. And of course that is a hell of a lot longer than your average car lasts. First question then is, how did this car get to be this way? It's doing just as well pretty much as it was when it was built. Answer is, it was built that way. It's built with corrosion resistant metal and really tough tires and all those good things. So that's very similar to the way in which a human body, the reason why the human body lasts so much longer than the body of, let's say, a dog or a mouse. All right? But actually the important thing about this slide is not the picture. The important thing about this slide is this up here, the title. There's a reason why I've put VW bugs up there. And the reason, very simple reason, is that there are just as many 50-year-old VW bugs driving around the streets of this country as there are 50-year-old Land Rovers. And the reason there are just as many is not because VW bugs were built to last. Here's one. This car was built in the same year as the previous slide. Here's one on the previous slide. All right, so what does that mean if we now go back to the human body? Essentially, this is what it means. And there's a third way, a third completely different approach to combating the phenomenon of aging, to postponing the pathologies of aging. In this approach, which I'm going to call the maintenance approach, we don't try to slow down this process here whereby damage creates pathology. And we also don't try to slow down this process over here whereby metabolism creates damage. Instead, what we do is we propose to uncouple those processes from each other, to go in and periodically repair some or most of this damage, so that even though it's being created, it no longer inexorably accumulates. It never gets to the level that causes pathology to happen. That's the concept. So let's look a bit about that. Why am I so keen on that? Why do I think it's so much more promising than the other two? Well, fundamentally there are two reasons for that, and they come down to the fact that the maintenance approach avoids the problems of the other two approaches. In the first instance, it avoids the problem of the geriatrics approach. Remember, the problem was that the geriatrics approach faces the problem of a downward spiral. You've got essentially accumulating precursors, that make the geriatrician's job progressively harder all the time. The maintenance approach doesn't have that. Remember that damage is by definition a set of ongoing, lifelong side effects of metabolism, so by definition it doesn't have any accumulating precursors. So the maintenance approach does not face this problem of the difficulty of the therapy getting harder and harder as time goes on. But also, the maintenance approach avoids the problem of the gerontology approach. Because here what we're saying is we're going to leave metabolism alone. We're going to let metabolism create various types of damage at the rate that it naturally does so. And that means that we don't have to understand much about that. We only have to characterize the damage itself and then figure out how to fix it. We don't have to understand much about how it's created in order to do that. So that's basically the bottom line of why I'm so keen on this approach. Alright, so now for some biology. And in order to introduce that, I'm going to tell you that actually there's a second reason why the maintenance approach is so promising. The first reason, which I have here, is, as I've just told you, it seems to target the weak link in the process that goes between being alive and being dead. The second reason is it turns out that damage is a lot simpler than either its causes or its consequences. This is my first really outrageous claim of the evening. I claim that all of the various phenomena that qualify as damage by the definition I'm using tonight, these intermediates, these side effects of metabolism that accumulate throughout life and eventually contribute to the emergence and progression of pathologies of old age, all of them can be classified into one or another of these 7 major categories. And these 7 categories are actual, bona fide, down-to-earth, concrete biological phenomena. I've used fairly colloquial language here in describing them, in naming them, but that's what they are, if we go from the top. So, junk inside cells, what's that? What that means is simply molecular byproducts of normal, essential metabolic processes that, for whatever reason, the cell does not have the machinery either to break down or to excrete. So those byproducts simply accumulate. They are sequestered, typically in a part of the cell called the lysosome. And of course, eventually, the cell doesn't like that anymore because there's too much of the stuff, rather in the same way that your house doesn't work so well if you don't take the garbage out for a month. So, your students, of course, let's say not for a year, right? So yeah, that's junk inside cells. You can, of course, have junk in the spaces between cells as well. There's a bunch of cases where that happens. You can have too few cells. What's too few cells? That's simply cells dying and not being naturally, automatically replaced by the division and differentiation of other cells. So, these are pretty straightforward, as I say, concrete biological phenomena. And their connection with the pathologies of old age is quite well understood at this point. So if we go from the top, junk inside cells is basically why we get cardiovascular disease. It's a particular type of junk, oxidized cholesterol, basically. There's another type of junk that causes the main type of blindness in the elderly, age-related macular degeneration. If we go down to junk outside cells, there's a material called amyloid that accumulates in various organs. The type of amyloid that accumulates in the brain is believed to have a role in Alzheimer's disease, and obviously Alzheimer's disease is a disease of old age. Too few cells, loss of cells, is the ultimate cause of Parkinson's disease. There's one particular area of the brain that's affected in that way. And so on. You get the idea. So, first of all, I want to say, why can I be so confident that this really is an exhaustive classification? There are no 8th and 9th categories. Well, one reason is this. It's been the same list for nearly 30 years. All of these 7 phenomena have been extensively discussed and experimented on by gerontologists over at least this amount of time, since the early 80s, and in many cases a lot longer. And we've come a long way in that time in terms of our ability to analyse biological systems, figure out what they're doing, what they're made of. So you would really have thought that if there were lot more categories to identify, that we would have started to extend this list by now. Now, I grant that that's a somewhat circumstantial argument, but it's still quite compelling. However, we can give a more direct argument. We can say, well, okay, by definition, damage can only accumulate in long-lived structures. If a structure, a protein, say, or a cell for that matter, is damaged and then the thing is destroyed, then that damage is gone, so it's not accumulating. And you'll remember that accumulation is a key aspect of my definition of damage for tonight. So, you could just say, well, okay, what are we made of? We're made of cells and stuff between cells. What are cells made of? They're made of DNA and protein and so on. And if you just do that and you say, okay, where can damage accumulate? And what damage actually does accumulate in those places, then you get pretty much this list. So that's pretty good news. But of course, really, that's only first step. It's all very well to be able to describe the nature of the problem we want to solve in a bit of detail, to break it down into these sub-problems. But then we've got to figure out whether we can actually solve these sub-problems. So the good news is that I believe we can in the foreseeable future. Thanks very much. So on the left-hand side of this table, we have pretty much the same list that I had on the previous slide. We've got, in fact, it's exactly the same list, albeit written in different words and in a different order. So on the right hand of the table, we've got potential solutions to these things. Not just potential solutions, solutions that I think we have good confidence we can actually implement within the next few decades. And as I said, I don't have time to go into all of them in detail, but you can see the sorts of things that they involve. So, of course, you've all heard of stem cell therapy. Ultimately, what is stem cell therapy for, in a nutshell? What it's for is repair of this type of damage, cell loss. When a cell dies and is not automatically replaced by the division of a cell that's already in the body, we can put a precursor cell in ourselves, and that cell will divide and differentiate to replace the cell that went missing. That's stem cell therapy. And if we go down this list again, you can describe these things in very concrete terms, what they actually consist of. So that's pretty good news. But as I said, in order to describe them in detail, it would take far too long. I mean, the really good news is not just that we can give little names to these things, but that we can actually describe, as I say, a whole chapter in my book is dedicated to each of these phenomena and these potential solutions. So we can say a great deal about how we're going to do all this, about what we already know, what we can already do, and what the route is, what the most promising looking route is from here to there, so to speak. So what I'm going to do by way of illustrating that is I'm going to just talk about one of these 7 areas in a lot more detail. And I'm going to choose this one here, just because it's fun, really, and also because it's one of our flagship projects. Intracellular junk, molecular garbage inside cells. So I already told you that that's a really important aspect of aging. It's the ultimate cause of the #1 cause of death, namely cardiovascular disease. It's also the ultimate cause of age-related macular degeneration, and it affects elsewhere as well. And what I'm going to tell you about is this thing here, transgenic microbial hydrolases. Alright, so first of all, let's understand what the problem is that we're trying to solve in slightly more graphic terms. In cardiovascular disease, what happens is that white blood cells of a particular type, a cell called a macrophage, infiltrate the artery wall to gobble up detritus that's hanging out there, stuff that was circulating in the bloodstream, taking stuff from one place to another, and that's got stuck in the artery wall. And macrophages are extremely good at doing that, and they do it very well. They do it very thoroughly. But there are some contaminants, some toxic molecules that form a small proportion of this detritus. In particular, there are oxidized variations on cholesterol. And those toxins are not handled very well by the macrophage. And eventually they turn the macrophage into a sort of undead white blood cell called a foam cell. This is a foam cell. A foam cell used to be a macrophage, but now it can't even process things that it would normally be able to process, like normal native cholesterol. And you can see what the basic reason here. This is what's called a lysosome. It's a part of the cell that's responsible for breaking things down and also for the garbage recycling that macrophages have to do in the artery. And it's no longer able to do that. And that is the first step towards atherosclerosis. You get an accumulation of these cells that have become poisoned by these toxins. So what can we do about it? Well, about 12 years ago, I proposed that we might be able to do something seriously good about this, very effective, by adopting some technology that had never previously been used on anything biomedical. It had only ever been used in a completely different area of biology, namely environmental decontamination. So it turns out that you can use bacteria to get rid of pollutants. The idea of doing that is called bioremediation, and it comes from a concept that was put forward back in the 1950s actually, which basically said that there's probably going to be bacteria out there that can break down unusual substances, by which I mean simply substances that most bacteria can't break down. The reason there's going to be that variety in the world, in the environment, with regard to what things bacteria can break down, is because if you're a bacterium and you can't grow as fast as other bacteria nearby, then you're in danger of being made extinct. But you can avoid that. You can carve out a stable ecological niche by eating something that the fast-growing bacteria can't eat. So it turns out that this works. It turns out that bioremediation is not only an academic concept, but actually a thriving commercial discipline. You've got people out there using it to clear up disused airfields that have got TNT in the soil. You can use this method against plastics and against dioxins and even rubber. So it's very, very cool. But what's it going to do with medicine? Well, basically what it's got to do with is that there are environments that are enriched in human remains, right? And those environments, therefore, ought to be enriched in these recalcitrant, hard-to-break-down compounds that accumulate in various tissues in the aged human body and that cause us all these problems. But those substances are energy-rich. In other words, if you're a bacterium, you can actually live off these substances just so long as you have the machinery to break them down. So I reasoned that maybe we could actually find such bacteria, especially in environments, as I say, that are enriched in human remains. And that we might be able to make use of those bacteria. Now, what I did not suggest, and do not suggest, is that we should actually identify such bacteria and then simply inject them into the bloodstream. I think that would probably be counterproductive. But what I think might be very effective indeed is, first of all, to identify how these bacteria are doing what they're doing. In other words, to identify the genes and enzymes that they are using to break down the substance of interest. If we can do that, then we have the option to modify our own cells just a little bit, to add a couple more genes or enzymes to those cells so that they're breakdown machinery, the catabolic machinery as biologists like to call it, is augmented, and they can break down things that they can't normally break down and that are responsible for these diseases. That was the concept. So it took a while for anyone to understand the word that I was saying, of course, as it usually is the case with pioneering ideas, but we have made great progress recently. This is the idea, I mean, putting in simpler graphical terms, you've got this process, this process just turns young people into old people, and eventually into dead people, and then over here you've got a completely different process that turns dead people into decomposed people. And that process is mediated by the microbial ecology of the environment. So what we've got to do is figure out how this is happening and do straightforward, cell biology, molecular biology, and use that information to modify our own cells. So this is my absolutely horrible cartoon of a neuron, and thereby combat the process that turned young people into old people in the first place. All right. So does it work? You bet it works. This is actually some data from the first paper that was published from work funded by SENS Foundation about 3 years ago now. And what we did here was we wanted to find bacteria that could break down this particular chemical here, 7-ketocholesterol. That turned out to be public enemy number 1 in atherosclerosis. There are a lot of different variations on cholesterol that are bad for us and that do accumulate in the artery wall and make foam cells, but this one's the most important in terms of toxicity and abundance. So it's the one we really want to hit. And what we've got here is an experiment in which we took 7 strains of bacteria that we'd isolated from the environment, and we simply asked them to break this stuff down. In other words, we gave them some of this stuff, and we didn't give them anything else to live off. Right? So it was what's called an enrichment culture. And as you can see, nothing happened for 5 of these strains. They just sat there like lemons doing nothing, because they couldn't grow, and the 7-ketocholesterol hung around too. But the other 2 strains had a whale of a time. They had the genetic wherewithal to actually break this stuff down, and after only 10 days it's all entirely gone. You don't even need a microscope to figure out what's happened. So that was all very cool. And that is step 1, find bacteria that do the business. The second step, as I mentioned, is find how they do it. And there are various ways to go about that. So on this slide I'm showing one way that we've gone about this, which is mass spectrometry. Essentially what we're doing here is identifying the breakdown products of these bacteria. In other words, the substances that they create as a result of breaking down the target substance. And from that one can deduce what enzymatic reaction has occurred, and thereby, using standard bioinformatics, one can identify candidate genes that are involved. We've been quite successful using that approach. Another approach that has also worked for us is comparative expression analysis. In other words, identifying genes that are simply turned into proteins more powerfully when the bacterium is given this substance, and which are not overexpressed when the bacterium is given a similar substance that we don't want to break down. So in this case we might use native cholesterol. That's all pretty good news. Then what? Well, we've got to get, as I said, we've got to get these genes into our own cells and see what they can do there. And of course we start off in doing this in cell culture, in a petri dish, in the lab. We do things like this. We create engineered genes in which the gene that we are proposing to use to break down these things is flanked by various things that take it to the right part of the mammalian cell. That's something we have to do because a mammalian cell is a lot more complicated in its structure than a bacterial cell. So we do that sort of thing, and we basically get the right result. This is a typical experiment in which, first of all, we've got a stain that lights up the parts of the cell which we want to get our gene into. This is into this thing called the lysosome. And here we have another stain that lights up our engineered gene itself. And then we've got this superposition that simply shows that it's working, that the 2 things are in the same place. So, that's all very nice. Then, of course, we've got to show that the gene is not only going to the right place, but that it's actually still working. Sorry, the enzyme. And our preliminary experiments in this area are looking pretty good in that regard, too. So, over on the right-hand side, we're giving cells a humongous amount of this horrible stuff, 7-KC, and even if they have construct, our gene, nothing much happens. All the cells die pretty quickly, so this is basically just background. But if we put in smaller amounts, modest amounts of this toxin, then we get a much better result. All you really need to take away from this graph is that in each case, the last bar, the bar on the right, is higher than the others. That basically just says that the cells are surviving better, are more resistant to the toxin if they've got our construct than if they haven't. All of these other ones are various control experiments where they don't have the construct, or they have the construct but it's broken in some way, or they have the construct but it's not targeted to the right part of the cell, and so on. Alright, so that's pretty good news. But I want to emphasize that this is a big old experiment. It's a long project, this. It's a long research program. What I've told you over the past few minutes is that we are pretty good at step one, isolating bacteria that can break down the substance that we'd like to get rid of in the human body. We're also pretty good at step two, figuring out how they do it. We are getting good at steps 3 and 4, targeting these genes to the right part of the cell and making sure that they still work. But I want to emphasize that the data I just showed you on that is very preliminary. We've got a long way to go to really be good at steps 3 and 4. And that means I think we're going to be still a couple of years before we get down to here, which is an absolutely essential next step, namely actually doing this whole thing not on just cells in culture, but on live animals, on mice. And it's only when we've got that really working well that we can start thinking about clinical trials, about doing all this in humans as well. So it'll be a while before this works. And you may think, well, that's awfully hard. Why don't we just try and think of something easier so that we can get treatments for this sort of thing sooner, even if this easier thing might not work quite so well? And I would agree with you if we had such a treatment that could be developed more quickly and would not work quite so well. But the actual situation is that there is nothing out there, no alternative, either in existence already or coming down the pipe, that will work anywhere near so well. These diseases of old age, these storage diseases as we like to call them, are absolutely recalcitrant to treatment. The best things we have now are pathetically poor. You've got preventative approaches like statins that just mildly postpone the progression of atherosclerosis. You've got surgical approaches like stents that are, just hopeless. We've got to do this. We've got to develop therapies that are really hard to develop, even and not be scared that they're going to take a long time. The sooner we start, the sooner we'll finish. So that's why I wanted to spend so much time on that particular approach. I hope you've got the message that we're doing very solid, very real biology here, with a very clear plan that has a realistic chance of delivering extremely dramatic results in the foreseeable future. So now I'm going to stop talking about biology per se. The rest of the remarks I'm going to have for you tonight are actually more about technology than about biology. And as you will see, they're mainly about the history of technology and what we can infer from the history of technology about the future history of technology. So, you may have noticed a couple of things, well, a bit of a disconnect in this talk so far with regard to the efficacy of these therapies. On the one hand, a little while ago I had this slide, which gave you all these things that we think we can do, and I think that we've got a 50% chance of developing all of these things to a pretty good level of effectiveness within the next 25 years. So I want to emphasize that could be wrong. Like as for any technology that is more than a couple of years away, really, any prediction about time frames is extremely speculative. I would say that there's at least a 10% chance, therefore, that we won't get there for maybe 100 years. I don't care about that, I don't mind about that, because the fact is a 50% chance is quite enough to be worth fighting for. But still, 25 years, I think we can get these. And remember, because these therapies are repair and maintenance therapies, in other words, rejuvenation therapies, they're going to be in time for people like you. They're going to be, if we do develop them in that sort of time, available when you guys are only in middle age. And people who are in middle age are precisely the people who are going to be the beneficiaries of these therapies. They've accumulated a bunch of damage. They haven't really sunk into the pathologies of old age yet, but they're not very far away from it. And those are the people that we want to fix up. We want to bring back to a lower biological age so that they've got longer before they get the pathologies of old age. However, as you can see at the top of this slide, I am proposing that this will not cause indefinite longevity. I'm saying that these therapies will be able to confer only perhaps 30 years of additional healthy life. Now that, of course, is nothing to be sneezed at. I think that would be wonderful. And I've given it this name, robust human rejuvenation. But the disconnect, of course, is that the title of my talk mentioned the phrase defeating aging. And defeating aging is a lot more than simply adding 30 years, postponing the health of old age by 30 years. So the question then is, what more have I got to say? Do I actually have a reason to use the word defeating aging and actually mean it? And the answer is yes, I do. Sorry. Yeah, here we go. There is a third reason why the maintenance approach is so promising. I've told you, as you will recall, two reasons. Number one being it seems to target the weak link between being alive and being dead. And number two, that weak link seems to be a lot simpler than either the metabolism that causes it or the pathologies that are the result of it. But there's a third reason why the maintenance approach is so cool. And that is that repairing damage buys time. Now I'm going to spend a few minutes explaining exactly what I mean by that. And I'm going to do it with the help of this really quite horrible schematic. So first of all, I want to say I'm just putting this up here to explain a concept. Please don't try to take anything too quantitative out of what I'm showing you here. But what I've got here is a representation of normal aging and of the effects of rejuvenation therapies. So on the x-axis I've got age, on the y-axis I've got this thing reserve. Reserve is actually not a new concept that I'm introducing here, it's simply the opposite of damage, the reciprocal of damage. You can think of it as the amount of damage that someone can afford, the amount of additional damage that someone can afford to accumulate before the pathologies of old age start to happen. So that means the red line is a simplistic representation of normal aging. Age 0, you've obviously got not much damage, lots of reserve, time goes on, aging happens, you accumulate damage, your reserve goes down, eventually you hit this horizontal dotted line that I'm calling the frailty threshold, and that's the point when pathologies start to emerge, and of course after that you haven't got very long to go. So the pink line that I've got here is the representation of what I've told you so far. That we're going to take people in middle age, let's say this person is here, and we're going to fix them up reasonably well. That's what the first segment of the pink line denotes. We're going to fix a bunch of their damage. And after that, because we have not, as you'll recall, we have not actually done anything to slow down the rate at which damage is created, that means that aging thereafter happens at the normal rate. That's why this line has the same slope. This second segment of the pink line has the same slope as the red line. Well, of course, then we can repeat the therapies. We can use them again and again and again. So that's what this is showing. Bit of a problem. Each time we use the therapy, it doesn't work as well as what it did before. That's a bit of a problem. Because, of course, it means that we're not going to get indefinite postponement of aging. And you can see why the therapies hit diminishing return. It's very clearly depicted here. The reason is because the therapies are not perfect. The therapies, when we apply them here, they fix a bunch of the damage. Let's call it the easy damage. But there's all this other damage up here, the difficult damage, that is not being fixed by these therapies. And of course that difficult damage is going to carry on accumulating unabated, so that eventually, on its own, however well and however thoroughly we fix the easy damage, the difficult damage is going to tip our hero over the frailty threshold. Alright, so now I want to come to this business about maintenance buying time. The interval between the first and second applications of these rejuvenation therapies to any particular individual is going to be quite long. It's going to be maybe 15 or 20 years, as you can see. Now, 15 or 20 years is a hell of a long time in technology, including, of course, biomedical technology. So, we've got to ask ourselves, what can we actually expect that the second rejuvenation of this person is going to look like? And the answer is that it's not going to look like this. It's not going to be the person getting the same old therapies that were available 15 or 20 years previously. What's going to have happened in that time is the therapies are going to have been improved in terms of cost and convenience and so on, but also in terms of comprehensiveness. So they're going to be able to fix up the easy damage, but they're also going to be able to fix some proportion, as you can see here, a half, of the difficult damage, the damage that they could not fix 15 years previously. And if that happens, then you can see the result. After their second rejuvenation, this person is actually not only more thoroughly biologically younger than they would have been if they got the old therapies, they're actually biologically younger at this point than they were when they got the first rejuvenation, even though, of course, they're actually chronologically older. So that's pretty good news. And you can see exactly why it's good news in this graph. You just don't get diminishing returns anymore. Over the long term, these people get biologically younger as they get chronologically older, and the amount of damage never gets anywhere near the frailty threshold. So that's why we can really talk about defeating aging. Why we can say that it's possible with these therapies, with rejuvenation therapies, to actually postpone the ill health of old age not just by 30 years, but indefinitely. Even though, in this scenario, the therapies themselves never actually reach perfection, they never actually can fix all the damage, nevertheless the impact in terms of the incidence of pathology is absolutely the same as if they had been 100% perfect from the beginning. Alright, so that's pretty dramatic. The question then is it going to happen? What is the prerequisite? Now you can see here that there's a minimum rate of progress required. There's a minimum rate of increase of the comprehensiveness of these therapies that would be needed in order that the general trend here will be upwards rather than downwards. And that concept, that cusp, is such an important concept that I've given it a name. That's the thing that I've been calling longevity escape velocity. So if we write out in words what the definition of that thing is, here it is, and it looks pretty nasty. You know, the rate at which these rejuvenation therapies must be improved following that first step where we get a reasonable amount of extra, well, let's say 30 years of extra healthy life, in order to stay one step ahead of the problem. A lot of words, but as you saw on the previous slide, it's a very easy concept once you draw it out. Alright, so the big question of course is, are we going to actually achieve longevity escape velocity? Or would we actually need an infeasible, unrealistic rate of improvement of the efficacy of these rejuvenation therapies? So I'm now going to give you a couple of reasons why I believe that it's absolutely 100% certain that we will indeed achieve and maintain longevity escape velocity from the point at which we have these initial first-generation rejuvenation therapies that give 30 years of extra life. First of all, I'm going to make a comparison with simple man-made machines again. I'm going to use aeroplanes this time rather than cars. Because the history of powered flight over the past century or so is a very interesting precedent. And it's by no means the only one. I could have used pretty much any technology that's been developed in recent history. You may say, well, hang on, this isn't biology, but it doesn't need to be, because what we can learn here is, this is legitimate, admissible, relevant data. What we can learn here is something about what to expect in terms of the rate of progress of another technology in the future, namely rejuvenation technologies. The big thing I want to emphasize here is, about the history of powered flight, is that it illustrates the fact that there are two major types of technological advance. There are fundamental breakthroughs and there are incremental refinements of those breakthroughs. Now, fundamental breakthroughs are very, as I mentioned earlier, very, very hard to predict in terms of when they're going to happen. Leonardo da Vinci probably thought that he was only a decade or two away from getting his machines off the ground. But of course he was wrong, and lots of other people were wrong for the next few centuries. But the Wright brothers were right, and here they are. But after that, it was a completely different story. After that, powered flight could be improved in terms of its efficacy by small steps, by incremental refinements. And when you've got that situation, it seems that this unpredictability goes away, that progress is pretty smooth, and certainly that it's pretty much faster than anyone would have expected. I bet the Wright brothers were dead surprised when it took only 24 years to to fly solo across the Atlantic, which is Lindbergh, of course. And 22 years until the first commercial jetliner, 20 years until the first supersonic airliner. Now you may be thinking, well, hang on, where's my flying car then? But of course we know the answer to that. We can't be bothered. Commercial flight. There isn't the commercial pressure, the public pressure to actually develop commercial flight beyond the sophistication that we managed 40 or so years ago. That won't be the case with regard to therapies that keep people from getting Alzheimer's disease, I can assure you. But I grant that it's circumstantial evidence. It isn't biology, as I mentioned. So I thought, well, it would be good to have something more direct. And so what I did a few years ago was I worked with someone to get a computer simulation done of this. We went back to this definition of aging that I've been working with all evening. And we said, well, okay, we'll write a simulation that works this way so that we can then ask what would happen to the simulation if we introduce these therapies. And of course, this is all published. I'm perfectly happy to email anyone a copy of the paper. But the bottom line is illustrated here. So these are survival curves, as they're called. A survival curve is simply a graph showing what proportion of an initial population is still alive at any particular age. So the black line here is not a simulation. The black line is actual real data of, I think it was US males in 1999, something like that. And so what we've got here, as you can imagine, is everyone by definition is alive at age 0, and almost everyone stays alive until age 50 or 60, at which point people start dropping like flies and hardly anyone gets past 100. All right. So that's a regular distribution of death that you would have expected. Now look at the dark blue line for a moment. The dark blue line is a depiction of the simulated population. In this case, the population has the same intrinsic risk of death at any particular age that the people in the black line had, but they get these rejuvenation therapies. But they only start getting them in their first initial form at the age of 80. Okay? So that, of course, is why the two lines are coincident until down here, because, of course, half the people are dead before the therapies come along. And after that, you get some benefit, but only a little bit of benefit. And I want to focus on that for a moment, because it brings me back to something that I said at the beginning of my talk. I don't work on longevity, I work on health. When you're 80, you're already not very well, almost certainly. Which means that your risk of death is considerably higher than it was when you were 30. So, these people simply have a high risk of death, and because the therapies in their first forms are not completely comprehensive, they just don't get the upper hand fast enough. These people are ending up spending a good few years of life in a frail state of health, and therefore with a high probability of death each year, and therefore, cumulatively, they just don't have any chance of getting out the other end. But now let's look at this sky blue line here. That line denotes the same population, a simulated population of people based on the black line with the same intrinsic risk of death, but they get these rejuvenation therapies. But in this case, they start getting them 10 years earlier, in other words, at the age of 70. And you can see the story is pretty much the same at first, not a lot of benefit, but eventually, for those lucky people who do live long enough, the therapies do start to get the upper hand, because they're beginning to get comprehensive enough. And as you can see, eventually maybe 10 or 15% of these people get out to the age of 150 or 200, and by that time, they have become so biologically young adults really, that their risk of death from aging has disappeared, gone to zero. Zero. There is no depiction in this, and no representation here of death from causes other than aging. But what this means is, unequivocally, longevity escape velocity. If you're 60 when the therapies come along, in the first generation therapies, that's the brown line here, and you can see nearly half the population manage it. So that's pretty good news. But here's the real kicker, the really good news on this slide. The really good news is that in this particular run of the simulation, I was ludicrously, insanely, ridiculously over-pessimistic with regard to the assumptions about how rapidly the therapies would be improved. Here's what I said, right? I said that the therapies would be doubled in their efficacy. That means we halve the proportion of damage that can't be fixed yet. only every 42 years. Now, 42 years, I mean, for crying out loud, that is the interval between Lindbergh and Concord. That gives you an idea of exactly how ludicrously pessimistic it is to suggest that we would only achieve a doubling of efficacy of these therapies in that time. But even if we did only achieve that, we still get unequivocally longevity escape velocity. All right? So what I'm telling you is, yes, it's a rather counterintuitive concept. Yes, it seems rather bizarre that we would go from a world in which the average longevity is going up very slowly, only by a couple of years per decade, into this, hitting this absolute, like something like a singularity really, an absolute step function where suddenly lifespans become indefinite. Just like that. But the fact is, it is mathematically, and this is data, it's mathematically inescapable. It is vanishingly unlikely that this would not happen, just so long as and when we get those first generation therapies that can give us just 30 or so extra years of healthy life. So I kept banging on and saying I don't work on longevity, but people always ask about what it means for longevity, so here is what it means. The world record longevity right now, the world's oldest recorded verified person, was 122. She died in 1997. Her name was Jeanne Calment, and she was fantastic. She spent the last, at least decade of her life being exceptionally old and having journalists come around to her house, her nursing home on her birthday every year, and they would always ask the same tedious question. They'd always say, "What's your secret?" And she would always come up with a new answer. And it was always a good answer too. My favourite one was when she was 120. She said, my secret is I gave up smoking when I was 117. And it wasn't even true. She only gave it up for 6 months. And then she said she wanted to go back. Anyway, thing is, 122, right? So we won't get anyone out to 150 without developing these rejuvenation therapy, the robust human rejuvenation that gives these first 30 years. But once we're there, once we've done that, we will have done the hard part. That's what longevity escape velocity tells us. So that means that people who are not much younger, maybe 20 years, maybe 10 years younger than this first pioneer who gets out to 150, will be getting out to 150 in good health, in large numbers. In other words, they will have truly reached longevity escape velocity and been restored to young adulthood, and that means they can live indefinitely. So how long does indefinitely mean? Well, we can do a calculation. We can ask, if in today's Western world you are, let's say, 26, today's your 26th birthday, what is your chance of not reaching your 27th birthday? And of course the answer is pretty low. It turns out to be around 1 in 1,000 or less. So, all we need to say is, okay, how long will people live on average if they maintain that probability of death each year not increasing with time, irrespective of how long ago they were born? And, of course, the answer is in 4 digits. Actually, of course, that too is a ridiculously pessimistic assumption. What do we die of when we're 26? We die of things like car accidents. Well, I'm not working on stopping people from being hit by trucks, but plenty of other people are. Right? So, actually, this number here is an extremely conservative estimate of how long people would be likely to live. Some people don't like me saying this. I get a lot of blowback from people who would like to call themselves politically astute, and I call them politically cowardly. They say, and also the media, of course, let's face it. I mean, if you've read about my work in the media at all, you will probably have seen articles whose title has the word immortality in them. And, that annoys the hell out of me, because it does trivialise all of this. It does. I mean, it's done for a reason. It's done in order to, if you like, help the reader to maintain some kind of emotional distance from the thing and treat it as entertainment. But the fact is, it doesn't help at all, because it does make the thing sound like entertainment, it makes it sound like science fiction, and that means people don't care enough about it, and that means people don't agitate to make it happen sooner, and that costs lives. I've said so in print a number of times, and I've really put the back up a lot of my colleagues, who have tended to say things like this about what I say, but it's scientifically absurd and irresponsible and so on. I rather like this one down here. I was introduced for a talk once that way. But the fact is, to my mind, it's these people who are the irresponsible ones, because it's slowing things down, it's costing lives. So finally, how can you stop that? How can you make a difference? First of all, I mentioned I've written this book. It's a few years old now, but only a few. It's still pretty up to date. And if you're not a biologist, it is tough going. It's pretty hardcore, but you can get through it, because it does not make any prior assumptions, it doesn't use a lot of jargon or anything. And if you are a biologist, you will definitely not be disappointed that it cuts corners or anything. Absolutely everything's in there. So I hope that this book will be of interest to a lot of you. Because it's written for a general audience, it's not very expensive. And and I do encourage you to get the paperback edition, because it came out 12 months later than the hardback edition. And in those 12 months, so much had happened, so much progress had been made in all of these various areas of biotechnology that we need to move forward in order to implement all of this, that we had to write an entire new full-length chapter just to cover 1 year of advances. So, that was pretty encouraging. Finally, what else can you do? Well, I mean, if there are any, billionaires in the audience, please see me later. Because we are a charity. I mean, no matter how small, it's not written for nothing. We do obviously encourage small donations as well as large ones. But it's not all about money. It's also all about how the money is used and how other people's time is used. So, if you are a biologist and you're wondering what particular field of research to go into, for example, find something that's actually relevant to all of this. Write to me if you want and ask me more about what specific fields you might go into and where you might study and so on. If you're a journalist, interview me, get the word out. If you're a conference organizer, get me up on stage. That sort of thing. Everyone can do that sort of thing. Absolutely everybody, because you don't necessarily need to do it in a professional capacity. Everyone can do advocacy. You can all talk to your friends, your colleagues, your family. You can always get people to take this seriously. It takes persistence. People will try to change the subject. People really don't like thinking about this. People in general have made their peace with aging. They just don't want to think about it. They feel, it's inevitable, it's horrible, they've got to put it out of their minds, and they've become very good at putting it out of their minds. That used to be a very sensible, rational thing to do when aging really was inevitable for the foreseeable future. But we are now within striking distance of doing something about aging, and that rationalization approach has become an enormous part of the problem. So I want all of you to be going out there and seriously doing something about this. I want you to be getting active, getting people to really think and get annoyed about aging, and get enough money spent to push this research forward as fast as it ought to be going, which is not happening at the moment. There is simply not enough willingness to understand that aging can be brought under medical control. But I hope I've been able to convince you tonight that it can. So I'll stop there and I'll be happy to answer questions. Right.
Interaction with all this coinciding with the allowance of medical procedures to take effect in the economy, which is to say, how does the FDA affect all this, along with the requirement for regular testing?
Right, that's the question. So the question is, how are we going to actually get these things made available once they've been developed, given how hard it is to get even one drug through the FDA and how much money it costs to do so? And this is a very cogent question, because for sure, if these therapies were taken through clinical trials and into the clinic within the regulatory regime that we're familiar with today, then the time frames that I'm describing here of something like 25 years from now would be very over-optimistic. We will probably need to get, it could easily be 50 years. So what's the catch? Well, what I say is, the good news is that we are going to have some lead time. Even if it takes a few more years, there will be a point, I think it's going to certainly be in less than 10 years, when results in the laboratory, in mice, become sufficiently impressive to cause a sea change in public expectations of what's going to happen in the future. Essentially what's needed is for the results in the laboratory to be good enough that most of my colleagues, even the colleagues that I've been disparaging up here for disparaging me, will be willing to go on camera and say, yes, it's only a matter of time before regenerative medicine really works for humans. Aubrey de Grey was right all along. When that happens, it's going instantly to become impossible to get elected unless you're willing to have a war on aging, unless you have a manifesto commitment to do that. Because, as I say, this whole business of pretending that aging is actually a good thing or not wanting to think about it is a coping strategy for a situation in which one doesn't really believe that one's going to be able to benefit from future medical advances in this area. When that belief goes away, the stupid rationalizations will also go away overnight. Alright, so what does that mean in terms of actual public policy? What it means is the public will not tolerate anything that slows down the availability of these drugs. There will be a whole new re-evaluation of what is really wanted. And in relation to the FDA, what that means, I think, is that there will be a move to approve drugs at a much earlier stage of testing. Probably equivalent to phase 2 now rather than phase 3. That will mean that the cost of developing a new drug or a new intervention will be reduced by at least a factor of 10, and the time to do so will be reduced by at least a factor of 3, which is the sort of thing that we really need. Now, of course, there's more to it than the FDA. We've got to have, for example, a great deal of investment in the creation of increased medical infrastructure to deliver these therapies when they come along. So that means training a lot more medical personnel, it means building a lot more buildings, and so on. Big question. But it's going to happen precisely because, even with the best possible situation in the science, there will be at least a decade between the identification, the development of really proof of concept versions of these therapies in mice and the development of those therapies in humans. Next. Yep.
Well, one of the fundamental things in your theory about the longevity state velocity is this kind of continuing innovation. And one problem that I see with that is that this essentially leads to companies, which are ostensibly going to be the organizations that are delivering these therapies, are going to be continuously renewing patents and creating new technologies that they have proprietary ownership over. And that's going to just continuously be driving the cost of these therapies, or keeping them at a high level, which might deny accessibility to these technologies.
Okay.
What is there in order to be able to make these things, these longevity technologies, these treatments available to everyone?
Okay, so the question is very closely related to the previous question, actually. The question is, might we have a difficulty in terms of availability of these therapies arising from intellectual property, arising from patent ownership and restricted availability, and therefore potentially high prices of these things? And really the answer is very much the same as the answer to the previous question. Ultimately, everybody, whether it's even big pharma, they work within the context of the legislation of the countries in which they work. And that legislation is created and altered by governments, and governments do what they're told by the public in democracies, because ultimately all they really care about is getting re-elected. So all it's going to take is for the public to be sufficiently angry. At the moment, the reason why companies do end up restricting access to, whether it's medical technologies or anything else for that matter, in their own interest, is because the public doesn't care quite enough that they're doing so. If the public did care, it wouldn't happen. So I believe that this is going to be, I sometimes use the phrase war on aging. Okay, I think that's not an exaggeration. I think it really will be what we can think of as a wartime mentality here, in which people are willing to accept very different policy changes and what changes in the way society works, just in order to end the slaughter as soon as possible. That's my belief. Next. Yep. Yeah, white shirt.
You're talking about regenerative therapies. Are you going to specialize those therapies for every different type of cell? And if so, that would be cost effective?
Okay, so the question is, how many of these regenerative therapies are we going to need? Are we perhaps going to need a vast number of them because different cell types are different and different people are different and so on? And the answer is, we're certainly going to need a lot of therapies. And one of the big differences between the delivery of these technologies to people and the delivery of today's medicine will be that. The fact that today, doctors and medical professionals try to keep things simple. And it's just not going to be possible. We are going to have to do a lot of simultaneous treatments. However, I'm not too worried that the number of treatments will go completely out of control. First of all, everyone's going to need the same treatment. Hands up anyone in the audience who doesn't have aging. Okay, right? So and if we think about, and I'm not being frivolous there, the point is, even if we look at the rate of accumulation of these various types of damage, there's not all that much difference between different people. So I mentioned the world record age at the moment is 122. Not many people die of age-related problems below the age of 60, right? So that's only a factor of 2. So it may very well be that rather than diagnosing any of this, we just go in and give everyone these treatments often enough. And yeah, we're treating some people twice as often as they need, but so what? Now in terms of cell types and so on, yes, within each of those 7 categories I talked about, there's likely to be a number of examples. I've already told you with regard to junk inside cells, talked about 2 examples, one for blindness and one for cardiovascular disease. We're definitely going to need different enzymes for those 2 problems, identified from different bacteria, a whole new parallel research project. But of course, there is a great deal of economy of scale there, because the development of the therapies and indeed the nature of the therapies when they are developed will have a great deal in common. You know, it's a bit like stem cell therapy. Stem cell research is a big field because different tissues need different stem cell therapies. But it's still a field because different stem cell therapies also have a great deal in common. So I'm not too worried. Yep.
Based on technological innovation, what the base of it is, the base of that innovation makes you predict that we will have the first therapy in, let's say, 25 years. What in the past decade were the scientific breakthroughs that amazed you the most? That could prove your...
So, I'm sorry, I didn't get the last sentence. Say again.
So what in the past decade are the breakthroughs?
Okay, so the question is, in the past 10 years, what are the breakthroughs in biotechnology, biomedical research that have led me to be so optimistic about these time frames? And, well, actually, to be honest, most of them are the ones that we've all heard about and that we're all impressed by. Things like the development of induced pluripotent stem cells. In other words, the ability to take a regular non-stem cell and regress it back into a very primitive state so that one can use it to create pretty much any cell type of the body that one likes without having immune rejection. That's certainly one example. There have been a number of advances in the development of new viral vectors to deliver DNA for somatic gene therapy. One of the biggest advances over the past few years has been the development of a whole new approach to tissue engineering, to creating artificial organs, which involves taking an organ that might not even come from a human being, and maybe from a pig, for example, and removing all the cells, but leaving the vasculature in place, so that then this scaffold can be repopulated with new cells, typically, of course, taken from the prospective patient, so again, avoiding immune rejection. That's an approach that solves pretty much completely what has historically been the #1 problem of tissue engineering, namely giving your new cells enough blood supply, a good enough blood supply, so that they don't all suffocate before they actually sort themselves out. So there's quite a number. Yes, guy in the black shirt.
I remember you making in your TED talk an argument about evolution does not care about aging. So can you reiterate that? I mean, how is aging not an evolutionary consequence?
Okay, so the question is, why do we age in the first place? Why has evolution not just got rid of aging for us, or more or less? What's in it for aging? And yeah, this is a very important question. Way back in the 1880s, when evolution had only just been invented, a very famous German biologist named August Weismann started to think about exactly this question. So, well, okay, look, evolution is obviously far cleverer than we are. That's actually something that Francis Crick said some time later. Therefore, the fact that we've got aging that tells us that evolution must have invented aging on purpose. There must be an evolutionary fitness advantage to the species for having aging, such that a species that got rid of aging would not last very long. And he came up with a nice explanation involving competition between the young individuals of a species. But it was completely wrong, because what it presumed was that what it requires in order to work is that there should be enough old and physically and mentally impaired individuals in the population for evolution to work on. That's to be some. And Peter Medawar, back in the 1950s, so after a full 60 or 70 years when this idea had gone pretty much unchallenged, pointed out that actually in the wild, because of such high mortality from other causes, there are virtually no old individuals in most species, and therefore the whole thing just can't work. So then the question is, what is the answer? Why do we have aging? And Medawar said, well, okay, maybe the reason we don't have aging is not because evolution wants us to have aging, but because evolution doesn't not want it badly enough to have actually taken the trouble to do anything about it. And if we look at what that actually means in more detail, it actually comes out looking very plausible. Because what we certainly do have, is a whole bunch of automatic, built-in, anti-aging machinery. Machinery that does automatic repair of all manner of different types of damage that do accumulate, that would accumulate otherwise, that don't accumulate, would accumulate if we didn't have that machinery. So, in order to live longer, what we need is even more anti-aging machinery. We have better anti-aging machinery than a dog or a mouse, for example. Therefore, evolution has got to want to create that machinery and then to maintain it. And the problem is, of course, that all of our genes are subject to a constant bombardment of mutations, including in the germline, in other words, sperm and eggs leading to the next generation. So if you've got really, really good anti-aging machinery that's going to let us all live to 1,000, okay, but then ultimately we're only actually living to 30 because we're being eaten and freezing to death and starving to death and so on, then what's going to happen very quickly is that the genes encoding this really good anti-aging machinery are going to accumulate mild mutations that make those genes work a bit less well. In other words, allow the damage to accumulate a bit more quickly. And that means that we end up reaching old age at only 700 and then 400 and so on. And this process will continue until until aging does become a problem for death. In other words, until the damage is accumulating fast enough so that some people are getting into a point of having an increased probability of death just because they were born a long time ago, even despite the other competing causes of death, the starvation and hypothermia and so on. So that's the standard explanation now. Medawar actually said it in a way that was oversimplified, because as I say, you do actually need some old individuals in order for the process not to continue, right? But it was further refined thereafter, and basically everyone says what I've just said now. This is not something that I'm saying that's controversial. But yes.
You had a whole list of possible therapies to treat aging. What do you think is the one that's closest to being something that can sort of be applied, and where you want research to happen?
Right, so the question is, which of these therapies here, you can probably still see it if the lights are on, are closest to actually being developed? Now, first of all, I want to emphasize that really, it doesn't matter which one is closest, because we've got to get all of them working reasonably well until we get a result in terms of healthy longevity. But then again, it sort of matters because each of these things is important for some specific disease, so, that would be great. So, the top two are pretty close. There are examples of stem cell therapy that are in clinical trials already for particular human diseases, including in some cases age-related diseases. So Parkinson's disease I mentioned, there are stem cell trials for Parkinson's disease. Early stage, not really working very well yet, but getting there. Alzheimer's disease, there's a lot of things that go wrong in the brain in Alzheimer's disease, but one of them is the accumulation of this stuff called amyloid in the space in the extracellular space. And people want to get rid of that. It was only about 12 years ago that people figured out in mice that you could do this using vaccination. You could basically get mice, you could stimulate the immune system of the mouse brain, the microglia, to gobble this stuff up. That's all you need to do, because when this stuff gets inside the cell, it gets to the lysosome, and the lysosome is much more powerful at breaking things down than what any machinery is that we have outside the cell. So so that moved to clinical trials awfully quickly, and those clinical trials are actually very advanced now. They're in phase 3, so it's looking pretty good. The other ones down here are a lot further away. Any more? Yes.
What are the organisms might there be that things that have better anti-aging or longevity strategies or mechanisms? And is there any example of any work that's being done? Taking a look at that.
All right, marvelous question. So the question is, what other species could we learn from in terms of aging? I've talked about other species that we can learn from in a sort of lateral thinking type way. In other words, for example, bacteria that break down oxidized cholesterol. But of course, the bacteria don't break that down because they want to live a long time. So that's a sort of indirect reason why we would study other species. The question here is there are there other species that we could study for the direct reason that they already just, are better at not aging than what we are? And unfortunately, most of the things that look like good answers to that question don't really turn out to be good answers. One thing that we could look for is species that live a very, very long time, and certainly there are some. But those species don't have the same type of anti-aging problem that we have. Those species tend to be ones in which there is no cell type, no organ composed of cells that are long-lived. When I say a cell is long-lived, what I mean is the cell spends a long time not dividing. Okay? So, of course, in us, we've got the brain and the heart and one or two other places, especially those two though, which are very long-lived, and the cells are very long-lived. In fact, they last for the whole lifetime of the organism. And, I don't know about you, but I'm quite fond of my central nervous system, and I would not really want to, sacrifice it, even in the interests of not getting old. Because, we're talking about we're talking about plants, for example. Bristlecone pines, they live maybe 3,000 years or whatever, but they don't have a central nervous system. There are lots of... and the point is, none of the cells in a bristlecone pine has been non-dividing for more than, let's say, 30 years. This seems to be true of all these species. If we go slightly more modest and we ask, well, okay, let's look for a species that may not be absolutely non-aging, but it does pretty well. Unfortunately, even then, if we look for species that are more closely related to us, we tend to find that it's not necessarily clear that they're better at not aging, but rather that the problem they have is still a bit easier. So let's take whales. The bowhead whale in particular is known to live at least 250 years. And the big problem is oxygen. So breathing is clearly bad for you, right? It's in the process of consuming oxygen, we create free radicals which cause damage of all of the various types that I mentioned, oxidative damage. Whales just don't need to do so much breathing per unit volume, so per cell, because they have simply a smaller surface to volume ratio. They have to burn less energy per unit volume in order to keep themselves warm than what we do. So they just don't have such a problem with free radicals, so they don't have such a problem with the accumulation of damage. That sort of argument works across a lot of other species that we might look at. There are some species where I do think that we could learn something. For example, there are some birds that live nearly as long as we do, despite being smaller than us, and therefore having a higher surface to volume ratio and a bigger problem with free radicals, among other things. However, if we ask, well, how much better are they than we are, the answer is, well, not really very much. Maybe twice as good if we're lucky. And so what we would have to think about next is how we would use any information that we discovered in this way. And it's not looking too hot, really. Basically, what we might find out, for example, is that some particular protein in the mitochondrion, for example, is a slightly different shape than in humans. And that shape allows protection against the creation of free radicals when oxygen is metabolized. But then, what will we do with that information? Even if we had really good gene therapy, which incidentally we're going to need anyway for other purposes, we'd still need to get that protein to work in a foreign context, in a context in which it had not evolved. Every protein in the human body interacts with other proteins. It turns out that actually the metabolism of oxygen is a particularly bad case of this because the interaction is very, very intimate. So we would not expect this clever protein that we find in this other species actually to be so clever if we put it into our own body. In fact, it might very likely do more harm than good. It's just the sort of thing that I was talking about when I made fun of how complicated metabolism is early on in my talk. Next. Okay, the blue shirt at the back.
You spoke about the exponential increase in technology. Do you not foresee by the year 2050 or maybe 2100 that there's a cyborg race of humans beyond which point aging becomes irrelevant? And do you think that might be perhaps a simpler solution and a better use of resources than solving this very complex human age?
Okay, so the question is, won't we see, with regard to the exponential increase of technology, the emergence of and progression of, let's call it, non-biological solutions to medical problems that reaches a point of comprehensiveness, so that we just don't need our bodies anymore, and therefore aging is much less of a problem anyway? Now, first of all, I didn't really say anything about exponentially accelerating technology, and one thing that I forgot to mention is that longevity escape velocity does not accelerate. We don't find ourselves in a situation where, as time goes on, we have to carry on at an accelerating pace improving these technologies. In fact, the opposite is the case. The further we get in approximating, in approaching perfection in the comprehensiveness of these therapies, the more slowly we can afford to make the next steps, it turns out. So that's pretty good news. But the answer to your question is, yes, I think it is quite likely that we will increasingly see non-biological solutions emerging, and that they will play an increasingly important role in the overall panel of interventions that exist. It's conceivable, in the long run, that we might have a situation in which we can turn our whole body non-biological, though I think that's quite a long way off. Now, you actually mentioned in your question, you said, well, isn't it likely that we would do this in sort of 2050 or 2100? Well, possibly 2050. I think quite possible that we get there in 2100. But if those dates are realistic, then you've answered your own question, because that doesn't mean it would be a better use of resources than the approach I've talked about, because the approach I've talked about, I think, has a good chance of being in place by 2030 or 2040. Next. Let's see, who hasn't asked one yet? Guy in white over there.
So far, I guess the best documented anti-aging therapy has been calorie restriction in mice. Do you recommend that same treatment for humans? Is that the best? Should we all be doing that?
Yes, I see you have a vested interest. All right. Yeah, so the question is calorie restriction, which has been so successful in rodents over many decades now, is this something that I think is likely to have good benefits in humans? The answer is, I think it's probably going to have a non-zero benefit, but I think it's going to be much, much less effective in humans than it is in rodents. The essential reason why I think this is that ultimately we have to start from evolution, as usual. We have to ask, why does calorie restriction have a benefit in terms of longevity in any species? And if we ask that in terms of, mechanisms, what the actual fitness advantage is, the best thing we can say is that species have had to evolve in the context of unpredictable food supply, unpredictable incidence of famine. And they've got to optimize their evolutionary fitness in that context. So, the problem is that long famines don't happen so often as short famines. And there's a minimum frequency with which something has to actually be experienced by a species, below which any evolutionary pressure that might exist to respond to that environment, that experience, just isn't enough to make the stuff happen. You don't evolve the genetic machinery, or you don't keep the genetic machinery if you happen to have already got it. it just mutates into oblivion. So what this predicts really is that species with different natural lifespans will gain more or less the same absolute amount of additional life from the optimal amount of calorie restriction. So that very short-lived species will be able to do really serious molecular acrobatics and live a lot longer than they otherwise would. Medium-length species will get quite a bit, and really long-lived species like you and me will get virtually nothing in terms of when stated as a proportion. And that's exactly what we seem to see. So the short-lived species that one needs to look at are not mammals. The most obvious example is nematodes, Cenorhabditis elegans. And most of you probably know that it's possible to extend the lifespan of C. elegans by a factor of several, I think the record now is 10, by certain mutations. Now the important thing is these mutations are in pathways that are closely related to nutrient deprivation, particularly a pathway called the Dower pathway, which causes immature nematodes to go into basically a spore-like state, where they can stay for, again, several times as long as they naturally would before, and still be able to emerge and live a normal lifespan after nutrient availability returns. Mice can't do that. So mice are much less able to respond to nutrient deprivation than nematodes are. The only experiment that's been done on a species that lived as much as a decade is one experiment done with lifelong calorie restriction in dogs, and sure enough, they only got the same sort of absolute amount of longevity as mice and rats typically do. So yeah, I'm not all that optimistic. But, of course, the good news is that there are a bunch of very expensive experiments going on right now with regard to lifelong calorie restriction in monkeys. And those experiments in the next 10 years or so will actually tell us reasonably well whether calorie restriction, whether what I've just said is true. Next, over on the far left, on my left.
When you find a way to make regenerative medicine work, what do you think the implications are in regards to the population growing exponentially and depleting all the resources in the world?
Yeah, right. So I more or less answered that question, gave you my favourite answer to that sort of question right at the beginning of the talk, where I said there are no ethical issues here really. In other words, I have no idea what the actual answer to your question is. We could certainly happily spend all year coming up with scenarios that might be able to cope with overpopulation or with any other aspect of society that might be a problem that might hypothetically be created by solving the problem we have today. But the fact is we cannot know whether the problem that we might create will exist, let alone be big enough to outweigh the importance of the problem that we'll be solving, namely the suffering that comes with old age these days. And I personally think, if you ask me about specifics, that there are all manner of ways in which the problem of overpopulation caused by the elimination of aging would not occur. Just fertility rates coming down naturally, women on average having their children later and later and later, which of course affects the trajectory of global population. That would be, in my view, greatly accelerated by the elimination of menopause, which is one thing that's going to happen. There's then also, of course, the fact that we have other technological advances, such as, for example, nuclear fusion coming in to reduce humanity's ecological footprint, because we wouldn't be burning fossil fuels so much, and therefore increase the number of people that we can have on the planet without a problem, and so on and so forth. But really that's not the answer. The answer is we don't know, and therefore we have a moral obligation to develop these therapies as soon as possible so as to give humanity of the future the choice.
Yeah, but do you need this, when you're doing this, and when you are really close to solving regenerative medicine, do you think that other areas of the world have to, because, for example, if you say you do it in 2050 and it's widely used, the population is going to grow within months and years exponentially because people aren't going to be dying, but we're still going to be reproducing at the same rate. Does it feel more obligation to wait for other areas of the the world.
Okay, okay, so the question here is, well, hang on, you're going to have a very rapid increase in the population, therefore, should we perhaps slow down the rate of development of these therapies so as to let the relevant, necessary other technologies catch up? The big flaw in what that question assumes is the idea that the rate of increase in population will be rapid. It really won't. If you actually do the arithmetic, then you've got, well, basically, yeah, let's put it in a nutshell. We're still only going to be getting older at 1 year per year. You know, we weren't going to have, not going to have any 1,000-year-old people for 900 years, whatever happens. If you actually think about what this means in terms of today's population, here's something that not many people realise. Today's population, you'd think it was, you know, it's growing, but it's growing relatively slowly. It took 12 years, more than 12 years, to go from 6 billion to 7 billion. You might think, well, that means that there's a 20% excess of people being born over people dying. You'd be wrong. It turns out that as of today, more than twice as many people are born each day as are dying. More than twice as many, right? So that means that even if we had no way of solving all of this, we had to absolutely stop any population growth. And even if we eliminated all of death, not just aging, absolutely everything, then all we'd have to do would be to halve the birth rate, and we'd be done. Okay. Now, I'm using all in quotes, obviously. You know, I'm not saying that's easy, but it does mean it's something that we need to give humanity the choice to do. It's not something that we would necessarily need technologies for, and it will happen slowly, so we absolutely can't anticipate. So I don't think that your logic works. Come on, next. I'm a schedule now. Okay, guy in yellow.
Why have more old rich people bought into this idea?
What? Okay. The question is, why haven't more old rich people bought into this idea? And it's an excellent question, one which has been much on my mind ever since I started trying to persuade old rich people to give me money. But I guess the fundamental reason, I have to say, and it mortifies me to say this, the fundamental reason why most old rich people have not bought into these ideas is because they're old, and they don't think that it's going to be in time for them. And of course they're probably right, it's probably not going to be in time for them. But that's not the only reason. The other reason is that these people have been alive for a long time. In other words, they have been immersed for a long time in this pro-aging rhetoric, in the need to make their peace with aging because they don't think anything's ever going to happen to it. So, you know, these people are just hard to persuade. I certainly do find that the people who, especially the wealthy people who tend to buy into this much more readily are the young people my sort of age. So, yeah, I think that's basically it. Another thing is, you know, what's bizarre to me is these people don't really care about their kids either. You know, you say, well, okay, it might not be in time for you, but that, and they don't really care. But ultimately, the reason they don't care is not because they don't like their kids. Well, it might be sometimes, but because they really, really don't think it can be done, and they don't think it would be a good idea, and so on. They really have totally bought into this, making their peace with aging and being irrational about it. So I guess it's what is it now? It's nearly 9:30, so we ought to be going soon. I'll have one last question if anyone has one. But they don't. I guess, okay.
Yeah, so, you know, I lived in England for a while.
Mm-hmm.
And I think the culture is a bit different over there. I don't know, I think as a country, like America, is much more religious than England, right? Now, do you think that's an obstacle to this, like, war on aging you anticipate, that, you know, we have some...
Yeah, okay, this is an interesting question. So the question is, since religion is much more of a factor in public life and life in general in the US than it is in many other places in the developed world, might that be holding things back? So far, I don't think it's actually making much of an impact. I think that I'm not really even on the radar of the religious right at this point. I think it's just too inconceivable that any progress could be made in this area, so they don't see that there's any real need even to oppose me. Now, in principle, that could change. However, I've actually had a very gratifying set of experiences when I have discussed this topic with people who come at me from a religious perspective. All I do is I say, well, hang on, aging is bad for you, it causes suffering. Scripture, Holy Scripture, whether it's Christianity or anything else, is pretty unequivocal on the point that it's our duty to hang out down here and, you know, alleviate suffering as best we can until God calls time on us. And of course, God can call time on us. He can strike you down with a thunderbolt, however healthy you are. So we're not in any way, disrupting God's plan by defeating aging. And this argument turned out to be rather effective. I mean, I don't exactly get, fundamentalist Christians turning around and saying, "Oh dear, I hadn't thought of that." But they tend to go awfully quiet, put it like that. Yeah, so I think the opposition to this may actually be much more muted than one might initially expect. All right, thank you very much, everybody.